This talk's called The 10 Commandments of Reliable Data Science. We'll kind of chew through all the pieces of that and what they mean, but just to pick one, 10 Commandments, that's tongue-in-cheek. I think the reason that we all go to conferences like this and we talk about things like this is because everyone's interested in craftsmanship. So these really aren't commandments, they're guidelines, but in the real world, we'd have a beer and argue about which ones of these are wrong and things like that after the talk. But we can do that in Discord after this, and I look forward to talking about it. So let's jump right in. This picture is from a famous airline disaster where two experienced, respected pilots with well-trained crews collided, and a lot of passengers lost their lives. And it launched a whole field of accident analysis, which sort of inspires this talk. And it's about norms, culture, and quality improvement that ended up going from this sort of thing to making air safety one of the safest. And I kind of had a whole story prepared to motivate why we would even need this talk at all. But an interesting thing happened a couple days ago, which is that there was a sort of viral blog post about data science, a critical blog post that made the rounds and I think sort of proves the point. So if you want to hear about a bad data science project gone wrong at a big company, you can read the long version of this, which I'll link to at the end. But let's talk about the discussion that's been going on the last few days. This is a post called Goodbye Data Science about a practitioner who's moving on from the field to data engineering and had some critical things to say about the way we do things. And there were a lot of responses to this that were just sympathizing, echoing, saying things are even worse than this person was saying. And it was really eye-opening to see not just how data scientists think about their own field, but how data science is sometimes perceived in other parts of the organization. So some of the things people were saying were that analyses are often wrong and couldn't possibly be right because they were flawed from the beginning, or leak data. There are things that are incorrect that should have been foreseen. Or people think that data scientists take forever and produce work that's not valuable anyway. And so we need to take these things seriously, even if we're not necessarily having any of these problems right now on our team. It seems like there's something that bears more scrutiny in our field. And I want to just make the point that even if you don't have correctness issues in your projects, or that sort of data science problem that we'll talk about today doesn't happen on your team, the reason that I think sometimes people judge data science poorly is that from the outside, it looks sometimes pretty mysterious and artisanal. And the thing about engineering disciplines is they try very hard not to be artisanal. If you need to rely on heroics and you need to rely on everyone being unbelievably perfect, then it's not engineering. It's some kind of art form. And so for data science to be reliable, we need to get beyond this alchemy perception. So the way we come at this, our argument on my team has a few basic ideas. One is that data science work is a kind of software. And so we know from the field of software, and they're grappling with this for the last 50 years, that correctness and reliability of software depends in large part on the development practices of the people that make it. So data science quality depends on software engineering quality. And today, we're not really talking about code running in production. We're not really talking about MLOps or DevOps or randomized controlled trials. We're talking about the modal data science project, where a data scientist gets asked to look into something, and typically, and I know there are products that try to address some of these things, but typically the data scientist will open up a notebook, either on their computer or a server, and start working on the problem. So we're talking about that. And where is this coming from? Some of the thoughts here come from consulting, data science consulting, working with lots and lots of different organizations on lots and lots of projects and seeing how other teams do things. And also running competitions where we get to see how people that are amazing at the computational part, how do they organize code? What do projects look like in the wild? So let's dive right into the rules. The first one is maybe one of the most commonly experienced, and that's that projects are disorganized. So we need to start a project in an organized way and find a way to keep it organized. We all know this pain. You see a file, it has some weird name. It's sitting right next to a bunch of other files that we don't know where they came from or what order they should be run in. lots of data science projects are like this. It's just a fact. And I think a lot of this, it doesn't come from bad intentions, but it comes from an idea that we'll start, just playing jazz and then we'll clean it up later. And unfortunately, that somehow never really happens. I mean, there are a lot of papers and ideas about how to organize projects, and all of them are basically good if teams follow any guidelines at all. Almost that's an 80% solution. But we really take inspiration from the kind of Django model here. And if I start a Django project, everything's always organized about the same way. And so even if I'm coming to somebody's project that I've never seen before, I kind of know where the database models are going to be. They're in models.py. I know where the URLs are going to be. They're in urls.py. And the nice thing about that is that it enables us to collaborate. It's less artisanal. My project isn't some weird one-off thing I only ever did once. If I structure it in a repeatable way, other people should be able to figure that out. So we have a project that does this called Cookie Cutter Data Science, which is fairly popular out in the field. But it almost doesn't matter what template or project gets used, and there are a number to choose from. If the team is using one, the projects tend to stay much more organized. And a lot of times it's often no more than just a good file and folder layout, and sometimes that's enough. But teams can get really sophisticated about the way they do this. Doing something is more important. Another idea that we won't spend too much time on is that everything comes from somewhere and the raw data is immutable. And this is already generally fairly accepted, that you don't mess around with like the data extract or the original source data. But this idea of a directed acyclic graph, we talk about often in data science. But when it comes time for people to actually make sure that their projects obey this idea, it's a little bit less common for it to be well obeyed. And this kind of thing is something that we see a lot out there, where there's a file in the project that's critical to something, but I'm looking at it and I don't know where it came from, and I don't know how reliable it is, and where do we get a new copy when this one gets out of date? How do I know if it's out of date? And so on and so forth. And this is just endemic. I mean, it's kind of hard to find a project where you just open it up the first time and things smoothly flow from end to end. We'll talk a little bit more about tools for that in a minute, but we can't even get to those tools before we talk about version control. And at this point, this wasn't really true 10 years ago necessarily, but at this point, most teams are using Git or something like it. So the rule isn't really about using it at all. It's about how do we use it for the things specific to data science. A couple notes there. We think that data mostly should not be kept in source control. And often people don't do this just because they can't. If you try to add a really large file, your Git will have problems. But one of the problems with adding any files to source control, even kind of smaller intermediate ones, is that reproducible pipelines that don't get exercised tend to be broken. This is true where in DevOps, people kind of understand culturally that if you don't test your data backup system, it just won't work. And that's like a norm that people have. And there are a lot of ways and places to store files, but as long as teams adopt some practice that's standard across projects, it's usually okay. There are more complicated tools, but often just having a way to capture where data gets stored at all is more important. The other thing is that version control systems enable code review. And we'll talk more about this later, but now that there are a lot of teams are using GitHub or GitLab or Atlassian products, when you're using version control, we use code review. But in data science, sadly, a lot of times we don't do as much code review. Sometimes that's because it's a little bit harder to review the work. Sometimes it's just because the files are harder, like a notebook is a JSON file. And yes, tools exist, but do people use them? If you go out and you look around, people don't really use tools for those. So we have this project called NB Auto Export, which mirrors a .py file anytime you save your notebook. But really more important than what tool you use is just finding a way for the team to review each other's code so that there isn't a norm of just download the notebook and eyeball it. The next rule is maybe one of the most important, which is that notebooks are really for exploration, but source files are for repetition and automation. So notebooks, we all know what the benefits are. Most of us use them all the time. You can iterate rapidly, test out a lot of different things, interleave code and explanation. They're very visual. That's an excellent property, good for communication. But mostly teams don't use tools for running them in an automated way, which mostly means that for running them, it's a person opening up a notebook and doing the things. They're difficult for version control. We just talked about that a little, but they encourage repetition, which is another insidious issue, which is that if everything's in notebooks, it's hard to import from another notebook. So people copy things around and errors creep in that way. We see that all the time. I know someone's going to say Netflix runs notebooks in production. It's a really cool idea, and they seem to do it quite well. The thing to remember is Netflix has teams of people that maintain this tool and make sure it's running, and they have operation centers, and most of us do not. So the typical workflow is to have gigantic notebooks that do everything from loading to cleaning, transformations, model training, model outputs, and visualizations. And the problem with this is it involves an awful lot of eyeballing, and people get squirrely about moving up and changing some things and not rerunning all the things because some are slow and all of that stuff. And so when we do it this way, we add a lot of places that error can creep in. So a more balanced workflow is to use Notebook for what it's great at, which is getting rapid feedback, and looking at things. So when you get a piece working, if it's not the piece you're trying to look at, if it's utility code or some computational function you need, but is not really the point of the analysis, it makes sense to move it to a source file, a place that can be linted, version controlled, code reviewed more easily, and tested, which we'll talk about more. So rule 5, tests and sanity checks prevent catastrophes, and they are highly, highly underused in the field. That's understandable, because of all code out there, data science code is pretty hard to test. Sometimes it involves big data sets. Sometimes data changes, so your values change, so it's hard. What are you asserting if the value changes? We use randomness on purpose, and so things change, and tests usually assume you're testing something reaches an expected value. Visualizations are really hard to test, and notebooks just don't have the same amount of tooling for running and discovery tests. But that doesn't mean that we can't do it, especially if we're obeying the last rule, which is to move, often used or common functions out to source files. Now we can write tests. So here's an example of like a Haversine function, so distance on a sphere, and just some tests of edge cases. Nothing crazy. But what happens if it's zeros? What happens if some value is missing? And that's the kind of thing that isn't too big a lift, and we could be doing, but most teams are not. On that note, the idea of testing, what things work and what things don't. In data science code, we generally want to fail loudly and quickly when anything is off, instead of trying to handle exceptions, which is a big part of thinking about software engineering. And the reason for this is not because data science code is so fragile. The reason is because a lot of data science code is actually pretty robust to things happening in a way that's not desirable. So this cartoon, the reason it's funny is because in a lot of our workflows, when we get the shape of the data right and all the things run, if everything kind of multiplies out and there are no crucial logic errors, you'll get numbers. You can force the machine to give you numbers, but are they right? That's harder to ensure. So, and this is just a known property of systems that use any kind of probabilistic modeling, which is the whole reason they're useful is they deal with noise well. And so if noise is coming in, but we don't know it's coming in, that's a problem. And you can see this even in the very simplest case. You imagine that some part of our analysis involves like a mean of some values. Imagine there are a lot more of these and they're coming from someone else. We take the mean, we get a number. Great. This is good. But what if some of them start to be missing? What if they're missing in a non-random way that affects the conclusions of the analysis? The truth is that a lot of our tools will handle this gracefully, if not correctly, or if not in the way that we intend. And so when I get this number out, it looks just like the number I got a second ago, but this has different properties, and this can be catastrophic. So one way of thinking about this is to test all of the assumptions that we're implicitly or explicitly bringing to our functions. And this is called assertion testing. And it's underused, I think, but part of that is because in normal software engineering, assertions are viewed, especially in production code, as like a red flag, meaning that this is something for testing and it shouldn't be here. Whereas in data science code, there are a different set of assumptions. It's a different kind of code. So actually, these types of assertions can be lifesavers. It means that, yeah, your code will fail, but if it fails, that means someone's going to look at it, hopefully, and try to understand why it failed. So we don't want to work if we shouldn't be working. And that's why adding lots of assertions liberally to a code base, especially if it's hard to test in unit tests or integration tests, just adding assertions that capture what we think should be happening can help a lot. There are packages that try to do this in a more Pythonic way, some more maintained than others. But basically, just the idea of defensive programming is something that I think we all can integrate into our workflows. Another is that project runs should be fully automated from the raw data to the final outputs. And this is kind of an interesting rule because it's hard to find people that disagree with this. People generally think that this is true. But on the other hand, it's hard to find data science projects, real world projects, not well polished sort of open source libraries and things like that, but real projects where it lives up to this aspiration. A lot of times there are steps, hopefully documented, but often not, that need to happen. And so you can't actually recover outputs, even if you have every other part of the project. People have thought a lot about this, going back to that idea of accident analysis. Dr. Atul Gawande, in his book, The Checklist Manifesto, was all about how human systems fail. And even if you've written down all the steps to this analysis or whatever, even if you know how to do it and you're the only one doing it, the point is that people get lulled into a false sense of security and steps get skipped. And people say things like, this has never been a problem before, until at some point it's a problem. Going back to the idea of the DAG representing our work as a graph, there are a lot of tools that do this, that turn that idea into something that can be run. And everyone kind of knows about these, but they're underused. If you see as many data science projects as we do, people have lots of just steps that aren't captured. Even if they're using the tool, a lot of times they just leave out steps. And so being able to turn that idea of a DAG into a command that you can run is an important part of ensuring the work that we do is reproducible and holding ourselves accountable. If you run it from a fresh environment, you can't reproduce the results. It's an indicator that you need to add more automation to the project. So just going back to this idea of a file, where did this come from? What situation would you rather be in? And this is a realistic situation because people do this both ways out in the world. Would you rather have that census shapefile, the instructions are written down in human language in a README, telling you do this, then do this, then do this? Or would you rather have it, even if you're not a big fan of make, would you rather have it documented in a make file where this target has a command that can be run? And then if the command fails, you know that it failed. I think that I may not always want to use make on every project, but being able to do this is an important property of a project in general. And so sometimes going back to the idea of fail loudly and fail quickly, the fact that you can run these means that if you delete everything that's intermediate and run it again, you see which parts are not reproducible and you can fix it. A lot of tools out there for this. They all have different trade-offs. The point is just using one, learning it, and making sure it's a norm on the team that the project's not done until all of the steps are part of that graph and can be run. Important parameters should be extracted and centralized. This is actually a norm that's growing in popularity, and I think a lot of the libraries that people use a lot have helped set this expectation. But just looking at this function signature for creating a gradient boosted regressor. There's this phenomenon that we call the problem of parameters, which is that even if you don't fill most of these in, they're options. And so in order to really reproduce someone's analysis, you need to know all of the things that went into this uh, right here at the time it was called. And in a lot of the projects that we see in the world, even for amazing teams, world-class teams, experienced data scientists, a lot of times you can't fully specify the behavior of the program without like 6 layers of places where these values could live. Environment variables, make variables, a central configuration file for the project, command line arguments, constants that live at the top of files, and then magic numbers or quarks that are just passed right where they're called somewhere in the code. And what we kind of recommend for this is to extract a lot of those values out to a central location where they are very visible and easy to change and easy to store in version control, and then look back later and see everything all in kind of one place without trying to do archaeology about what the environment was at that time, things like that. Relatedly, we think runs of a project, like runs of a data pipeline, even one for research. We're not talking about code running in production, but research code where people are doing experiments. Runs of the project should be verbose and result in artifacts. What do we mean? Well, looking at the typical workflow, we're working in a notebook. We change a bunch of things. We just look at the output cells with our eyes, and then we decide at some point whether it's good enough, and we're kind of thinking back about the last few hours and whether this is better or worse. And at a certain point, we run out of time, or we decide it's okay and we move on. With all the rules we've been talking about so far, that gets us pretty far. So we're testing, we're using an orchestration tool. We have our parameters extracted. Our life has been changed because we've tidied up a little bit, and we're feeling pretty good, but there's still something amiss here, which is that a critical part of this workflow involves eyeballing the results. And that is tough because even if your judgment is perfect, other people will have to pick this project up in the future. If it's valuable, it will live for a long time. And so that judgment doesn't transfer well. But also, it's hard to be right, especially when there's so much probabilistic noise and complexity in these projects. This is not something that feels good as a practitioner, and it doesn't build trust in the people who consume our work products. So just going back to the oldest days of computing, a log file is a powerful thing. And this is what we mean by verbose, which is just logging a lot of stuff and resulting in tangible artifacts, like storing this log somewhere so that you can look at it later, keeping it in version control. And this is just a toy example, but I want to pick out a couple things here. First is we're putting important bits of information all in one place. Could I look up what Git hash we were on at a certain point in time? Yes. But if I'm trying to understand a whole analysis, we want to put everything in one place. We can say what the random seed was. We can put the settings in here. Again, redundancy, just to make sure it's easy to understand. What rows were dropped, which ones were kept. And then when we get these things that just are ephemeral, like when you do a grid search over the best model parameters, at some point they're in memory, but often they don't get saved. Why don't we just save them? Create a place for the artifacts from a run to live. And that goes for the results as well. And if we capture the metrics, we don't want to be thinking, oh, did what I just do in the cell improve things or not? We want to look at the facts. Go look at the last run and see, did precision get better, but recall was worse? We want to have that put somewhere, and then write out the predictions. So maybe it looks like this. You can even copy the files around. It's not worth trying to save 4 KB if this is an important analysis. Copy the config file so you don't have to go on a Git archaeology expedition, and keep the log file right next to the predictions that came out. Which things get stored in version control? It's up to you. As long as there are norms on the team, almost anything sensible will work. And I know people are going to say, oh, well, this is why there are artifact stores and feature versioning and all this stuff. Yes, that's true. And a lot of teams should be considering those tools. But in practice, when people are just doing kind of exploratory work, those tools are not often in use. And this is a sort of middle ground where people can use the tools they're familiar with. Everyone's familiar with files, logs, settings that are in a machine readable format. And so that's a way that we can get a lot of the benefits without, convincing the IT department to buy a certain cloud product or something. And then finally, this one is great, not just for reliability, but also for the experience of doing work and feeling good about it. Is starting with the simplest possible end-to-end pipeline, going all the way from raw data to whatever it is we're trying to deliver at the end. And getting it, even if none of the individual parts are satisfactory yet, getting it in the form such that it produces something that we can almost deliver, so that then we can make educated decisions about where to spend our time rather than worrying about whether we'll ever finish this project. So imagine a project where we try to take raw data and visualize it. We sort of tend to work backwards and then think forwards. Oh, we need to get all the data, clean it all up, train a bunch of models, ensemble them, and then build an app. But this is waterfall. This is a dangerous game, because if any of these things get off track, then you may never finish. And so there's this philosophy that we want to get to the end product before it's good and get feedback, and that we implement things when we need them and not when we think we'll need them. So maybe we just use a little bit of data, some columns, a simple model, just take the predictions and, oh, look, we have a performance. This is a benchmark we can try to improve. And we start not with a visualization, but just printing in a table. So it looks terrible, but something happened here, which means we split this up into different concerns that can be collaborated on at the same time, as long as we understand what format the data is in. Now we can go back and change individual pieces and see our accuracy improve and change over time, and then decide as a team what parts to work on and what parts to leave.
Hello, we're almost done. If you would like to leave some time for the questions.
Yeah, great. So this is the data science process that's the ideal case. We can move around, we can play jazz a little bit, but still feel confident. And the reason that this is related to reliability and not just experience is that the faster we can get feedback and get things in final form, the more likely we are to discover defects before it's too late. So I invite questions, comments, angry pitchfork crowds. There's a long version of this that's on the site. The link is here, and I'll put the slides in Discord. And I'd be happy to take questions. We only have a little time now, but in Discord as well. Thank you.
Thank you very much for this very informative talk, and I've learned a bunch. Thank you.
Yeah, so Matt asks thoughts on NBDev. I've looked into it, and it looks great to me. There are a lot of projects that try to do this kind of thing. They each make different trade-offs. I'm in favor of projects like that, but it's my observation that most teams are not using them. And running cookie cutter data science, we often have people come in and say, here's my pull request. Everyone should be using DAT. Maybe they should, but the fact is that they're not. So if we try to impose this from the outside and say everyone should use this, it's not a successful way to build cultural norms. Good question. The thing to realize is a lot of these are aspirational, right? So I say these things with a straight face. My team, I personally don't always live up to these things. They're things to think about. So I think if you come to a team and you say, you guys are all messed up, we need to be adopting these practices. Right now we're doing alchemy and not engineering because this random person said so. That's less successful than saying, what are the painful things? Everyone knows the pain of census shapefile v2 new, use this for real final.xlsx, whatever. So starting with the pain points and trying to persuade with a vision of what things could be like is more useful.